Hello students, welcome to the video on photodetectors and LED of the module 2 of electronic devices subject. So in the previous class we have discussed in detail about what is a solar cell. So today we will be seeing what is photodetectors and LED. So in this video we will be seeing first about photodetectors. So what is a photodetector? So photodetector is a junction diode, PN junction diode, and it is a receiver, optical receiver. So whatever light energy it receives, that is the light energy which falls on the device will be converted to electrical energy. So here it is called as optical to electrical converter. It is a fundamental of optical receivers. Mainly it is used in digital communication where fiber optics technique is used. There are several detectors like photodiodes, phototransistors and photomultipliers. So in this video, we will be discussing what is meant by photodiodes. That is a diode when it is used to detect the light energy. When the photodiode is operated in the third quadrant, that is in the reverse biased condition, then the characteristics of the current is generally independent of the voltage, but it is proportional to the optical generation rate. That is, the generated current will be based upon the amount of light energy falling on the device. Such a device provides a useful means of measuring the illumination level or of converting the time varying optical signal into the electrical signal. What are the requirements for the photodetectors? So photodetectors should have a very good sensitivity and the desired wavelength and poor responsivity elsewhere. That is, it should be responding only for a particular wavelength of the light. So all the other, like it is like a filter, it should select a particular wavelength and that should particular light wavelength should be converted to the electrical energy. The next one is fast response time. That is, it results in high bandwidth. What is fast response time? The time taken to convert the optical to electrical form should be very fast and also compatible physical dimensions. So the device should be designed such that it is compatible for whatever applications we are using. It should be having low noise and insensitive to temperature variation, and also it should have a long operating life and reasonable cost. So these are the requirement of a photodetector. Now coming to the requirements, only photodiodes can be used in optical communication system, and because of this photodiode, there will be an conversion from optical to electrical energy, and since the conversion rate is very less in a normal PN junction diode, we go for an pin diode. Pin diode is nothing but a positive, intrinsic, and negative. That is, we will be having an intrinsic layer in between our P and N region. The main important thing here is you will be having a wider region to sense the electrical optical energy, but there will be no internal gain. So in order to improve the gain of the device for digital communication systems, we will be using the other type of photodiode, which is called as APD, or it is called as an avalanche photodiode. So here this is a schematic of an pin diode where we will be having a P region and intrinsic region and another N region. So this intrinsic region, even though it is having a small resistive, the resistivity will not be infinite. It will be having some resistance. The light energy which is converted here on this intrinsic region will be converted as electrical energy and it will result in the current which is called as in IR. The disadvantage of this PN or normal PN junction photodiode is overcome by this pin diode, and and also this results in increase in the current due to the intrinsic layer. So the next one is when we go for an avalanche photodiode. So we know that the gain which is getting due to this pin photodiode will be very less. It will maximum it can have an efficiency of maximum efficiency is one, where the efficiency is given as the JOP is nothing but the current density due to the optically generated current, and POP is nothing but the number of photons which is shining on this device. So this we can find out that the efficiency is very low. So in order to improve the efficiency of the system, we go for avalanche photodiode. So avalanche photodiode is internally multiplying the primary photocurrent before it enters the following circuitry. That is, internally, after the optical energies are converted to electrical energy, the converted energy will be multiplied by the avalanche process, and then it will be coming out as a current. So due to that, there will be an gain in the ionization, I mean the gain in the carriers, which is formed due to the optical energy. And here we can have different types of photodiodes. So heterojunction pin photodiode is nothing but where carriers are generated in the intrinsic layer, and then you will be having p plus and n plus region where which will be having different band gap. So light of an energy less than the band gap of indium phosphide can easily reach the intrinsic region, and the P and region have P and N have a higher band gap than the intrinsic region, so their absorption coefficient is of this can be used to alter the high radiation that would show up in the noise. So the next case is when we go for an different wavelength, that is when we go for different material, each material will be having absorption coefficient of different values. So the different colors gives here, for example, gallium arsenide, if I take for different wavelength, we can see the absorption coefficient will be varying. So based on the application, we can choose a particular device for our particular material for the photo reduction application. So the next one is what is meant by LED. LED stands for light emitting diode. So in a material characterized by direct recombination, considerable light may be given off from the junction under the forward bias. So LED is a device in which is operated in the forward biased condition. So this effect is called as injection electroluminescence. So another important device that makes of the radioactive recombination in the forward biased condition is semiconductor laser. A very important metric of an LED is the external quantum efficiency, neta into external, which is defined as the light output divided by the electrical input power. So here, if I take a normal PN junction diode, normal PN junction diodes comes under the indirect band gap. So indirect band gap is nothing but it will be having a change in the momentum before the electrons move from the conduction band to the valence band. In case of direct band gap material, we can see that the electrons when from the conduction band can go to the valence band directly with no change, no conservation of momentum, and hence it releases the extra energy in the form of light energy. So that is called as H into nu. So the wavelength of this light energy emitted, it is based on the material what is used to fabricate the PN junction device. So here, with the material characterized by the direct recombination, considerable light may be given off from the junction under the forward bias. Another, but the main disadvantage of it is called as is the incoherence. So to improve the coherence and on to make use of the radiative recombination, we can go for the semiconductor laser. When important metric of an LED is its efficiency, and the efficiency is found to be maximum in all the applications. The emitted photon from the LED have a wider angular distributions, and the photons incident on the semiconductor air interface at an angle greater than the critical angle would undergo total internal reflection and ultimately be lost via the absorption within the semiconductor. So a dome type encapsulation will be used so that the maximum number of photons are extracted. So this Doppler column gives us the different semiconductor material and what are the different material used for LED fabrication along with the wavelength and the color which will be emitted by the material. So here, for example, if you take gallium arsenide phosphide, it will be giving an amber color, and for if you take an aluminum gallium phosphide, it will give us a green color. And so here so here we can see that by varying the proportion of arsenic and phosphorus, we can go for various combination of LEDs of different wavelengths. Thank you.